The polished metal plate lay inside a vacuum chamber, cooled and shielded from stray currents, while delicate electrometers registered the faintest trickle of charge. Each time the wavelength of the incoming light changed, the stopping voltage required to halt the emitted electrons shifted in lockstep. No adjustment to the intensity altered that threshold. Dim violet light expelled more energetic electrons than the brightest red. The measurements accumulated, stubbornly repeating the same numerical pattern, experiment after experiment. Millikan varied the metal surface, changing work functions, cleaning and repolishing, probing for some hidden chemical or thermal effect. He altered the pressure in the chamber, checked for stray fields, and recalibrated his instruments with ritual precision. Yet the crucial relationship remained. The maximum kinetic energy of the ejected electrons increased linearly with the frequency of the light, and extrapolated to a cutoff that depended only on the metal itself. The brightness merely adjusted how many electrons appeared, never how energetic they were. The linear plots emerging from his notebooks traced an unwavering slope, numerically indistinguishable from Planck's constant. Each new data set tightened the uncertainties, squeezing out room for classical wave explanations. If light had been only a continuous wave, energy should have seeped into electrons gradually, regardless of color. Instead, the results behaved as if energy arrived in indivisible packets, with each quantum of light transferring a discrete burst to a single electron at the metal's surface. Gas flames and carbon arc lamps flooded new laboratories with a steady, brilliant glow, and carefully ground lenses focused these beams into razor-thin shafts. Glass plates etched with narrow slits, fine gratings, and knife edges sliced the light, sending it fanning outward in delicate patterns. On distant walls, pale screens showed crisply spaced fringes and halos, each bright and dark band matching the predictions of wave equations line by line. In lecture halls, chalk scratched across slate as professors derived Maxwell's equations, then pointed to their consequences with a sense of finality. The calculated speed of the electromagnetic waves matched the known speed of light to remarkable precision, and diagrams of electric and magnetic fields marched across the boards in right-angled oscillations. Light now appeared as a self-propagating disturbance in these fields, needing no material support, no flying corpuscles, only continuous waves spread through space. Researchers tuned coils, spark gaps, and metal plates, shaping invisible disturbances that leapt from transmitter to receiver. In darkened rooms, small sparks jumped across carefully spaced contacts whenever an oscillating circuit radiated, showing that electromagnetic waves carried energy from one apparatus to another. Standing waves formed between polished reflectors, nodes and antinodes fixed in place like ripples frozen in mid-air. Each new demonstration reinforced the conviction that light belonged to this same seamless wave family. In laboratories across Europe, researchers now tested Einstein's proposal with refined instruments. Polished metal plates sat in evacuated glass tubes wired to sensitive electrometers that recorded even the faintest currents. Beams of violet and ultraviolet light struck the surfaces, and electrons flew free, drawn toward collecting electrodes. Experimenters varied the frequency and intensity of the light, measured the stopping voltage needed to halt the electrons, and found linear relationships that matched the simple formula E equals hf with remarkable precision. Each new dataset deepened the tension with the classical wave picture. Increasing the intensity of low-frequency light flooded the metal with more electromagnetic energy, yet no electrons emerged once the frequency lay below a sharp cutoff. Meanwhile, even a weak beam of higher frequency light triggered immediate emission without any measurable delay. The electron's maximum kinetic energy depended only on the light's frequency, not its brightness, reinforcing the idea of discrete energy packets carried by individual quanta. Physicists, who had trusted the wave description of light, now confronted a stubborn pattern of results. The electric fields of the waves still explained interference and diffraction, yet the photoelectric effect demanded localized impacts, as if tiny projectiles struck the electrons one by one. Some researchers tried to preserve the old framework with modified theories of the metal's electrons, but the clean success of Einstein's photon hypothesis stood, quietly insisting that light possessed an unexpectedly dual character. In the quiet of the laboratory, the straight line on Millikan's graph stood unchanged, however often the measurements were repeated. Each point came from hours of watching faint currents rise and fall as the stopping voltage was nudged, then recorded. The workers around the apparatus adjusted lenses, polished electrodes, and baked out the vacuum chamber. Yet the relation between frequency and electron energy held. It ignored personal skepticism and experimental inconvenience alike. Different metals entered the chamber: sodium, potassium, clean sheets of freshly evaporated silver. Each time the line shifted sideways, but its slope remained the same. The threshold frequency moved with the metal's work function, while the proportionality between frequency and kinetic energy matched Planck's constant within experimental error. No change of surface, no adjustment of intensity, and no refinement of technique altered that shared universal incline on the graph. The light striking those surfaces still diffracted and interfered in other experiments, still spread and bent like any classical wave. Yet here, in the narrow space between electrode and plate, its energy arrived in indivisible packets. Electrons either escaped with a precise surplus of kinetic energy or failed to emerge at all. The apparatus revealed no half-absorbed wave, only discrete exchanges, as if each quantum of light carried a single fixed bargain of energy. As the rate of photons decreased further, each detection stood out in isolation, like a solitary mark on an otherwise blank canvas. Photomultiplier tubes and later solid-state detectors registered individual events with sharp electronic pulses. The apparatus remained unchanged, the same two slits, the same distance to the screen, the same alignment. Only the flux of light diminished, ensuring that at most one photon traversed the setup at any given time. On the detection plane, no sign of a wavefront appeared directly, only a growing constellation of scattered points. At first, the dots seemed randomly placed, with no obvious order. Over minutes and hours, as more photons arrived, bands of higher and lower density emerged in precisely the positions predicted by interference theory. Regions corresponding to constructive interference filled with many impacts, while the dark bands associated with destructive interference remained sparsely populated. Each photon had struck at a single, localized spot, never at two places at once, and never as a faint smear across the screen. Yet taken together, those discrete events built a pattern identical to that produced by classical waves. Calculations using wave functions and probability amplitudes matched the observed distribution with striking accuracy. The intensity at each point on the screen reflected not a continuous flow of light, but the likelihood of where each individual quantum had landed. Detectors stood beside the slits, waiting for passing photons. Each device had been tuned to respond to the faintest signal, a tiny click or flash, announcing which opening a photon had used. When the apparatus allowed such which path information to exist, the familiar interference fringes on the distant screen disappeared. The bright and dark bands gave way to two overlapping humps, matching the simple sum of two single-slit patterns, as if the wave-like character had been stripped away by the very possibility of knowing the path. Physicists then altered the apparatus so that path information could be erased. Polarization filters, oriented at carefully chosen angles, marked photons differently at each slit, making the routes distinguishable in principle. When those polarization tags were later scrambled or matched so that no measurement could reveal the original path, the interference pattern reappeared on the screen. The same photons prepared in the same way produced either wave-like fringes or particle-like distributions, depending only on whether the paths remained knowable in principle. The logic extended beyond light. In vacuum chambers and crystal targets, electrons emerged from guns as localized particles, struck detectors in isolated flashes, yet built up interference patterns when their paths were left undetermined. Davison and Germer saw electrons diffract from nickel crystals, while George Paget Thompson recorded ring-like patterns consistent with electron waves passing through thin films. When experimental setups tracked electron trajectories with sufficient precision, those interference structures faded, and the impacts arranged themselves as though only individual particles had crossed. In 1924, a young French physicist proposed that the strange dual nature of light extended to all matter. He assigned every particle a wavelength, given by Planck's constant divided by its momentum, so that an electron or even an atom carried a wave character. This new relation linked familiar mechanical quantities with the language of waves. It suggested that interference and diffraction were not exclusive to light, but could arise whenever particles moved with well-defined momentum. Within a few years, a new equation described how such matter waves evolved in time. Its solutions spread, bent, and interfered much like ordinary waves, yet no mechanical medium oscillated in space. Max Born reinterpreted the wave's squared magnitude as a probability density, assigning to each point in space the likelihood of detecting a particle there. For photons passing through slits, a broad probability pattern extended across the screen, while each detection still appeared as a single localized impact. As the theory advanced, the electromagnetic field itself was treated as fundamentally quantized. Photons emerged as discrete excitations, like individual steps on an otherwise continuous staircase. The same mathematical objects that generated wave-like interference also governed the chances of each quantum being absorbed or scattered. Classical waves in water or air required moving matter. Quantum waves encoded probabilities in abstract space, yet their interference dictated the precise distribution of the seemingly random, particle-like events. In the dim laboratory, a single faint click from a photon source signaled another trial. A lone photon impinged on the beam splitter and, according to the quantum description, occupied both arms of the interferometer at once. No apparatus marked its path. No detector waited in the middle of either route. At the outputs, two counters accumulated events whose relative rates rose and fell in a sinusoidal pattern as mirrors shifted, revealing interference in the statistics, not in any visible fringe. Then a shutter closed over one arm, or a device imprinted a distinguishing mark on photons traveling along it. The interference vanished. The two output detectors now registered counts consistent with ordinary particles choosing one path or the other at the initial splitter. Adjustments to mirror angles no longer produced rhythmic swings in the detection rates. Each photon still arrived as an indivisible, localized event, but the collective pattern no longer carried the delicate signature of a coherent wave exploring both paths. Delayed choice arrangements extended this logic into unsettling territory. The photon entered the interferometer, while a fast optical switch or movable beam splitter remained undecided between keeping both paths coherent or separating them for which path readout. Only after the photon had traversed the arms did electronics trigger the final configuration. Yet the accumulated outcomes reflected whichever option had been chosen at the end. Interference, when paths remained indistinguishable. Particle-like distributions, when path information had been made available, in line with Bohr's principle of complementarity. Arrays of dark photovoltaic cells lay exposed under a controlled beam, each junction built from carefully doped semiconductors. Incoming photons struck the material, transferring their quantized energy to bound electrons. When a photon supplied at least the band gap energy, an electron broke free, leaving behind a hole and creating a mobile charge carrier pair. Internal electric fields swept electrons and holes in opposite directions, and a measurable current flowed through external circuits, directly reflecting the arrival rate and energy of individual photons. Deeper inside an optical laboratory, polished mirrors and gas-filled tubes formed the core of a laser. Atoms in the gain medium sat in discrete energy levels, selectively excited by an external pump. When one excited atom spontaneously emitted a photon, that photon traversed the cavity and triggered identical emissions from its neighbors. Each new photon matched the original in energy, phase, and direction. Between highly reflective mirrors, the light field reinforced itself into a coherent beam that emerged in a narrow, intense column, its stability governed by quantum statistics of the photons inside. Long vacuum arms extended from central stations at gravitational wave observatories, where lasers split and recombined into kilometre-scale interferometers. Interference fringes recorded microscopic shifts in mirror positions as passing gravitational waves stretched and squeezed space-time. At the same time, individual photons arrived in discrete clicks on photodiodes, contributing random shot noise that limited sensitivity. By injecting squeezed light and using single photon-sensitive detectors, researchers reduced quantum fluctuations, extracting faint signals from distant black hole mergers while accounting for every photon that entered and left the apparatus. In the early debates, Einstein's concern over light quanta collided with Niels Bohr's defense of complementarity. Arguments over the photoelectric effect, the reality of trajectories, and the meaning of a wave function unfolded in crowded lecture halls and private letters. Each calculation, each carefully designed experiment pressed against classical intuition. Interference patterns emerged from single photons, yet detectors clicked one by one, forcing a reconsideration of what, if anything, traced a path between source and screen. Copenhagen-style views treated the wave function as a tool for predicting probabilities, not a literal wave in space. Many worlds' approaches described every possible outcome as realized in branching histories, removing collapse at the cost of multiplying realities. Pilot wave theories restored definite trajectories guided by a non-local wave. Quantum field theory rephrased light as excitations of underlying fields, with photons appearing as quantized disturbances whose creation and annihilation followed precise mathematical rules. Experiments grew more delicate and more audacious. Weak measurements teased out partial witch-path information while still allowing remnants of interference. Quantum eraser setups encoded path markers, then erased them after detection, recovering interference within carefully sorted correlations. Single photon sources, entangled pairs, and ultra-fast detectors revealed the same pattern. Discrete energy transfers arranged according to wave-like probabilities. Light appeared as something deeper than either picture, shaping lasers, fiber networks, GPS clocks, and quantum technologies that relied on this strange, reliable dual nature.